In structural engineering, deflection refers to the displacement resulting from the deformation of a structural member under applied loads. For beams, this displacement occurs perpendicular to the longitudinal axis and is typically measured as the vertical deviation from the unloaded position. While strength ensures a beam can resist breakage-type failure, deflection is governed by the stiffness of a member, which refers to its resistance to deformation and determines its usability, comfort, and compatibility with non-structural elements. This is the reason why deflection considerations in structural design are referred to as serviceability considerations. Serviceability refers to a structure's ability to perform its intended function under normal condition, which is distinct from safety against collapse. Excessive deflection can undermine the occupant's comfort, can damage finishes, or impair functionality, even if the beam remains structurally sound. In this video, we will discuss deflection in wood bending members such as joists and beams. We will begin with the engineering principles governing the analysis of deflection in wood beams. We will then look at how much deflection is allowed in wood beams. Finally, we will calculate the deflection on a garage door header and check if the deflection will exceed the maximum deflection allowed in the building code. Our discussion will be based on the provisions in the International Building Code or IBC and the National Design Specifications for Wood Construction or NDS by the American Wood Council, which are adopted in nearly all jurisdictions in the United States. Both the IBC and NDS may be accessed freely from the websites of the publishing entities. Please see the links in the description for access to the IBC and the NDS. The total immediate deflection in members such as beams, headers, and joists consist of two components. The first component is bending deflection, which accounts for most of the total deflection occurring on wood members under bending loads. The second component is shear deflection, which accounts for a small portion of the total deflection for wood members under bending loads. During analysis, the behavior of wood beams is typically modeled using the Euler-Bernoulli Beam Theory. The Euler-Bernoulli Beam Theory is a fundamental concept in structural engineering used to describe the bending behavior of beams under applied loads. It provides a relationship between the applied loads on a beam, its geometric properties, and the resulting deflection of the beam. The theory is built on the fundamental relationship between stress and strain for linear elastic materials, which means that it assumes that the material behaves elastically. Additionally, the theory is based on the assumption that the cross-sections of the beam along its length remain normal to the neutral axis, which means that there is no shear deformation. In this theory, bending moments create curvature in the beam, leading to deflection. All this means that deflection is a result of bending stress and not shear stress. The final equations used to calculate deflection that are derived from the Euler-Bernoulli beam theory are expressed in terms of the load acting on the beam. This is the deflection equation based on the Euler-Bernoulli beam theory for a simply supported beam or joist supporting a uniformly distributed load such as a floor joist or roof rafter. And this is the equation for a simply supported beam supporting a point load at the mid-span. There are many other equations provided in standard structural mechanics textbooks for beams supporting combined loading, multiple point loads, partial uniform loads, and other loading patterns and support conditions. These equations are typically based on the Euler-Bernoulli beam theory, which involves simpler mathematical formulations, making it easier to apply for analytical and hand calculations. Since the Euler-Bernoulli beam theory neglects shear deformations, it also disregards shear deflection. The question we need to address is whether structural engineers designing wood structures according to the IBC need to consider shear deflection in their designs. Additionally, if shear deflections must be accounted for, we need to understand how shear deflections are analyzed or incorporated into the deflection calculations for wood structures. For structural engineering in general, one alternative to the Euler-Bernoulli beam theory is the Timoshenko beam theory. The Timoshenko beam theory is an extension of the Euler-Bernoulli beam theory, and it was developed to address some of the limitations of the latter, especially when dealing with short beams or high shear forces. It accounts for both bending and shear deformation, making it more accurate than the Euler-Bernoulli theory in certain cases, particularly for beams with relatively short lengths and thick cross-sections. That being said, the use of beam analysis equations that are based on Euler-Bernoulli theory is much more predominant than analysis based on the Timoshenko beam theory. In many practical engineering problems, the differences in results between the two theories are minimal, making the simpler Euler-Bernoulli theory sufficient for design and analysis. Euler-Bernoulli beam theory involves simpler mathematical formulations, making it easier to apply for analytical and hand calculations. Additionally, the Euler-Bernoulli beam theory has been well established and widely used in structural engineering for centuries, leading to a vast amount of literature, design codes, and standard practices based on this theory. For wood design, especially for the design of dimension lumber and glulam members made from common softwood species based on the NDS, designers typically use equations based on the Euler-Bernoulli beam theory. As we shall see, the NDS makes special adjustments to the reference design values used in deflections equations based on the Euler-Bernoulli beam theory to account for shear deformation. At the heart of the Euler-Bernoulli beam theory and the Timoshenko beam theory is the relationship between deflection and bending stiffness. Bending stiffness is the product of the modulus of elasticity and area moment of inertia, or the second moment of area. Therefore, for the deflection of any member to be determined, the modulus of elasticity and the area moment of inertia of the member must be known. The modulus of elasticity used in deflection calculations is a material property of the species of lumber used. Modulus of elasticity values used in deflection calculations are provided in another publication of the American Wood Council known as the NDS Supplement. A link to a free copy of the NDS Supplement provided by the American Wood Council is provided in the description. The NDS Supplement provides design values known as reference design values for nearly all species of lumber that are commonly used in construction in the United States. For modulus of elasticity, the NDS Supplement tabulates two values for all species and lumber grades provided in the reference design value tables. One of those is a minimum value of modulus of elasticity known as E-min, which represents a 5% lower exclusion value on pure bending modulus of elasticity and a 1.66 factor of safety. This means that it is a very conservative value, which means that if you take a sample of individual lumber pieces of a particular grade and species and determine their modulus of elasticity through testing each piece, it is highly likely that all the pieces will have a modulus of elasticity that is higher than the value provided in the NDS Supplement for that grade and species. E-min is used to evaluate the lateral stability of beams and is not used in deflection calculations. The other much higher value of the modulus of elasticity is the reference modulus of elasticity, or E. This is the modulus of elasticity that is used in deflection calculations. Unlike E-min, which is a 5% lower exclusion value with a 1.66 factor of safety, the reference modulus of elasticity is an average value, which means that if you take a sample of individual lumber pieces and tested them to determine the modulus of elasticity, it is highly likely that some will have a modulus of elasticity exceeding this value and others will be less than this. Therefore, E is always higher than E-min, which is used in beam stability calculation. Please recall that we said that the NDS makes special adjustments to the reference design values used in Euler-Bernoulli-based bending calculations to account for shear deformation. In addition to being an average value, the reference modulus of elasticity provided in the NDS Supplement is also an apparent value. It has been factored to introduce a shear deflection component equivalent to that occurring in rectangular bending members with a span-to-depth ratio of between 17 to 21 under uniformly distributed load. This means that when a designer calculates deflection for sawn lumber and glulam bending members using standard deflection equations based on the Euler-Bernoulli beam theory but using the modulus of elasticity provided in the NDS Supplement, The deflection calculated includes shear deflection because the elastic modulus provided has been adjusted to include the effects of shear deflection. The ratio of the shear-free modulus of elasticity to the apparent modulus of elasticity may be taken as 1.03 for sawn lumber and 1.05 for glued laminated timber lumber. We have also said that the amount of deflection also depends on the area moment of inertia or the second moment of area. The second moment of area or the area moment of inertia is the quotient of the product of the width and the cube of the depth and 12. Deflection limits are provided in Chapter 16 of the IBC. Table 1604.3 of the IBC provides deflection limits for structural members under various load conditions including live loads, snow loads, and wind loads, as well as dead plus live load combination. These limits are expressed as a fraction of the member's span length. Typical expressions of these limits are L over 360, L over 240, L over 180, and L over 120. The limits are tabulated based on the type of member, the loading under consideration, and the supported elements. These limits are expressed in terms of the span of the member because deflection limits are dependent on the span and are not absolute independent numbers. Therefore, if the deflection limit is L over 360, a 30-foot beam will have a deflection limit of 30 feet times 12 inches per foot divided by 360, which is 1 inch. For a beam with a span of 15 feet, the deflection limit will be 15 feet times 12 inches per foot divided by 360, which is 0.5 inches. Therefore, we can see that although the two beams have the same deflection limit in terms of the ratio of the span to 360, the actual deflection is different because the two spans are different. When deflection limits are expressed as a fraction of the span, the higher the number at the denominator, the more strict the limit is. If we consider the 30-foot beam again, we saw that under L over 360, the deflection limit is 1 inch. If the limit is L over 240, the limit would be 30 times 12 divided by 240, which is 1.5 inches. This means that for L over 360, the member would have to be more stiff than is required under the L over 240 limit. Therefore, the higher the denominator, the more strict the deflection limit. According to Table 1604.3, roof members supporting plaster ceilings have a deflection limit of L over 360 under live loads, snow loads, or wind loads. This strict limit is intended to prevent plaster from cracking due to deflection. The same roof members supporting plaster ceilings have a deflection limit of L over 240 when considering long-term dead plus live load combinations. When supporting non-plaster ceilings, the deflection limit under live loads, snow loads, or wind loads is L over 240. For long-term dead plus live loads, the limit is L over 180. When not supporting a ceiling, the deflection limit under live loads, wind loads, or snow loads is L over 180. For long-term dead plus live loads, the limit is L over 120. Floor members have a floor live load deflection limit of L over 360 regardless of the finish material. When considering the effects of long-term loading including dead loads, the limit is L over 240. Exterior walls with plaster or stucco finishes are limited to L over 360 under wind loads. At the same time, exterior walls with other brittle finishes are limited to L over 240 and L over 120 when considering flexible finishes. Table 1604.3 also provides other deflection limits for interior partition walls, farm buildings, and greenhouses. The limits that we have looked at exist to ensure that structures remain functional and comfortable for occupants while protecting non-structural components, like finishes, windows, or partitions, from damage due to excessive movement. They are not provided to prevent collapse. Rather, they are intended to ensure continued usability. This is why deflection is referred to as a serviceability concern rather than a safety issue. It's about how the structure behaves, how much it bends, sags, or vibrates under typical, expected loads and not hypothetical extreme conditions. Excessive deflection do not mean the beam will break. Rather, it means that the building might not serve its intended purpose well. Since deflection is not a safety issue, the design against excessive deflections uses unfactored service loads. These are the realistic loads that the structure experiences during normal, everyday use, rather than the amplified loads used for strength design. One important question that may come up at this point is associated with the fact that bending and shear design, which are strength or safety design concerns, also use service loads under the allowable stress methodology just like deflection design. Where does the difference lie when we compare bending or shear design using service loads and deflection design using service loads? Bending and shear design using allowable stress methodologies compensates for the absence of load factors by factoring down the stress capacities using safety factors to produce allowable stresses that are several times lower than the actual material stress capacities. Therefore, the allowable stress methodology ends up achieving the same purpose as would be the case if the loads were factored, as is the case in the loads and resistance factor design methodology or LRFD. On the other hand, for deflection calculations which are always based on service loads, the elastic modulus reference design value provided in the NDS supplement is an average or mean value, as we have already discussed, and does not include a safety factor. Additionally, the calculated deflections are checked against limits in the IBC, which are empirical thresholds based on experience to prevent service issues. These limits do not have safety factors because deflection checks are not a safety issue. However, they do embody a certain level of conservatism derived from engineering experience and historical practice. Let us look at an example to illustrate the calculation of the deflection of a simply supported wood header that is subjected to uniform load. This is a 16-foot garage door header which is supporting a tributary width of 8 feet at the roof. For this example, we will check the adequacy of a 6x12 grade number 1 southern pine header in deflection. We will not check bending or shear. First, let us determine the properties of the header. Let us begin with the actual header dimensions. A standard dressed 6x12 beam is 5.5 by 11.25 in actual dimensions. The area moment of inertia about the header's x-axis is the quotient of the product of the width and the cube of the depth and 12. Therefore, in this case, the area moment of inertia is 653 inches to the 4th power. Let us now look at the section modulus. For a grade number 1 southern pine header or beam, the modulus of elasticity is provided in Table 4D of the NDS supplement. Please see the link in the description for free access to the NDS supplement provided in the American Wood Council's website. According to Table 4D, the reference modulus of elasticity is 1,500,000 pounds per square inch. According to the National Design Specification for Wood Construction, or the NDS, the reference modulus of elasticity requires adjustments to account for ambient conditions and the physical characteristics of the header. Please note that the NDS and the NDS supplement are two separate publications by the American Wood Council, and we have provided links for free access to both documents in the description. Table 4.3.1 of the NDS specifies that the adjusted design value for the modulus of elasticity is the product of the reference design value for the modulus of elasticity and the wet service factor, the temperature factor, and the incising factor. The wet service factor is provided at the adjustment factors section of Table 4A in the NDS supplement, and it is 1.0 in this case. The temperature factor is provided in Section 2.3.3 of the NDS, and it is 1.0 in this case since we are assuming that we will not have extreme temperatures for extended periods. The incising factor is provided in Table 4.3.8 of the NDS, and it is also 1.0 in this case since the header is not incised. Therefore, the adjusted design value for the modulus of elasticity is 1,500,000 pounds per square inch. This is the value that we will use in our deflection calculations. The next step is to work out the uniform loading on the beam. For dead load, let us assume a standard wood-framed roof with 1/2 inch plywood and asphalt shingles and a plastered ceiling. The dead load is approximately 20 pounds per square foot. Considering the 8-foot tributary width, the uniform linear dead load will be 160 pounds per linear foot. For live load, according to the IBC in Table 1607.1, the roof live load required for design is 20 pounds per square foot. Considering the 8-foot tributary width, the uniform linear live load will be 160 pounds per linear foot. For deflection, the IBC code requires that we check 2 deflection limits on Table 1604.3, which is provided in Chapter 16 of the IBC. There are actually 3 deflection limits, which include the limit when considering live loads only, the limit when considering wind or snow loads, and the limit when considering dead plus live load. Since we are using a plastered finish at the ceiling, and since the header is supporting roof rafters that are supporting the ceiling, the live load limit will be L over 360 and the dead plus live limit will be L over 240. The live load limit is L over 360. L is the span, which means that the maximum allowed live load deflection for this project is 16 feet times 12 inches per foot over 360. This is 0.5 inches. This means that when considering live load only, the deflection should not exceed 0.5 inches. Let us now calculate the actual live load deflection. We will express all factors using pounds and inches for consistency. The uniform linear distributed live load is 160 pounds per linear foot. This may be converted to pounds per linear inch by dividing by 12 inches, since there are 12 inches in 1 foot. Therefore, the loading is 13.33 pounds per linear inch. The span of the header is 16 feet. This is equal to 16 times 12 inches per foot, which is 192 inches. We have already determined that the modulus of elasticity is 1,500,000 pounds per square inch and the area moment of inertia is 653 inches to the 4th power. Therefore, the live load deflection is 0.24 inches. This is less than the maximum 0.5 inch limit that we have determined, and therefore the beam is adequate. Please note that by using the elastic modulus provided in the NDS supplement, the deflection we have calculated include a shear deflection component in addition to the predominant bending deflection component, even though the deflection equation that we have used is based on the Euler-Bernoulli Beam Theory. Finally, let us now look at the long-term deflection limit. According to Table 1604.3 in Chapter 16 of the IBC code, the dead plus live load limit is L over 240. Since the span is 16 feet, the deflection limit in inches will be the quotient of the product of 16 feet and 12 inches per foot and 240, which is 0.8 inches. Table 1604.3 also includes footnotes with important information about the dead plus live load combination. According to footnote D of the same table, the dead plus live load combination applies to the creep component of long-term dead load deflection plus short-term live load deflection. The footnote goes on to say that for lumber members that are dry at the time of installation and used under dry conditions, the creep component of long-term deflection shall be permitted to be estimated as the immediate dead load deflection resulting from half the dead load. This means that the code allows a load combination of 0.5 dead plus live load to be used instead of dead plus live load. For this example, we will be conservative and use the full dead load. According to Section 3.5.2 of the NDS, the total deflection under long-term loading consists of 2 components. The first component is the product of the creep factor and the immediate deflection due to the long-term component of the design load. This means that the first part is the product of the creep factor and deflection due to the dead load. The second component is the deflection due to the live load. We have already calculated the deflection due to the live load. Therefore, we will calculate the deflection due to the dead load and multiply the deflection with the creep factor, which according to the NDS is 1.5 for seasoned lumber used in dry service conditions. We already calculated uniform dead load, which is 160 pounds per linear foot. This may be converted to pounds per linear inch by dividing by 12 inches, since there are 12 inches in 1 foot. Therefore, the loading is 13.33 pounds per linear inch. If we use the deflection formula, the dead load deflection is 0.24. The total long-term deflection is the sum of the product of 1.5, which is the creep factor, and the 0.24 dead load deflection plus the live load deflection of 0.24 inches. The total long-term deflection is 0.6 inches. This is less than the maximum 0.8 inches limit for dead plus live load deflection, and therefore the header is adequate in deflection. We have shown that this header is adequate in deflection against both short-term and long-term deflection limits. If you enjoyed this video, don't forget to give it a thumbs up and subscribe to the channel, and do not forget to hit the notification bell so you never miss an update. Your support helps us keep creating great content, and we'd love to have you join the community. Thank you for watching.